All right. Hi guys, let's get started. So last time we talked about duality for linear programming. Okay, so the high-level idea is that to every linear program you can associate a corresponding dual linear program. They're both linear programs. Okay, if one of them is a maximization problem, the other one is a minimization problem. Okay, and so we saw an explicit transformation, and we stated without proof something called the duality theorem, which says that if the sort of primal, the original linear program, which is a maximization problem, has a bounded maximum, then its dual has a bounded minimum, and the solutions, the optima, in the two cases are actually equal to one another. Okay? And each of these kind of provides a respective upper and lower bounds that tell you how far you are from optimal. Okay? Now, today, we'll only very slightly skirt to the notion of duality. And today's lecture is sort of similar to the lecture of that we had 2 lectures ago on network flows, where we're studying a concrete algorithmic problem that turns out actually has a lot to do with linear programming once you look at it hard enough. Okay? And today we want to study something called zero-sum games. Okay? So that's the plan for today. Okay, let's start with an example. We're going to study rock, paper, scissors. Okay, so how are games typically represented syntactically? You must have seen them at some point, somewhere before. Not like board games, like games abstractly. Game tree. That's a reasonable thing. Some games are represented as trees. What's another way that you present? So, by the way, games that are represented as trees are games in which sort of players alternate to take moves. The particular games that we'll study today are called simultaneous games. In which all players, in this case, we're only going to talk about 2 players, so both players play once and simultaneously. Okay? Yeah? Excuse me? Right, an action matrix. So in general, if you have n players, this will be like some high-dimensional, so n-dimensional matrix that corresponds to all the possible simultaneous plays, right? So each player picks an action. But if we have just 2 players playing the game, like today, so today will be simultaneous and 2-player, then you can sort of describe what the 2 players end up doing as a matrix, right? Because every row will be what, say, the row player does, and every column will be what the column player does, according to their strategies. So in the particular case of rock, paper, scissors, we expect to see a matrix that kind of summarizes what the game does. So how many rows and columns would we expect this row to have, this game to have? 3 in each direction, right? Because also the game is symmetric, right? Kind of the 3 actions for one player are also the same 3 actions for the other player. So let's draw that. All right. So let's give names to these things. So this is going to be the perspective of the row player. And, OK, this is going to get in the way. And it's going to be the column player. And we're going to label each row for the row player by the strategies that it can play. So row player could play rock, it could play paper, it could play scissors, right? Similarly, for the column player, the column player could play rock, could play paper, could play scissors. Okay? Okay, this is only saying kind of what are the options for each player. It doesn't say once the players play, kind of what happens. That's kind of what we put inside each of these cells of the matrix. Okay? Now, let's say, for example, that both players play rock. What is it typically in rock, paper, scissors? What's the outcome? Right, it's a tie. So let's put 0. Right, that seems to be like a neutral outcome. Neither player wins anything. Okay? Let's say rock and paper. Or actually even easier, first paper and rock. Okay? So the row player plays paper. The column player plays rock. Who is winning? The row player. Okay, so it means that we have to so now we have to make some choice about what are we actually putting inside this, the cells. In zero-sum games, we're going to basically say that any unit of winning of one player is the same as a unit of losing for the other player. So we're just going to write A1 here. That denotes that the row player has won with utility 1, and at the same time, the column player has lost with utility 1. Okay, it's going to be symmetric. Okay, it's zero-sum in the sense that it cannot be that both of them are happy. To every unit that the row player is happy, there's a corresponding unit that the column player is unhappy. Okay, so by symmetry, what should we write in this other column here? -1, right? Because in this case, from the perspective of the row player, he is losing. Okay, so he's losing a unit of 1. Okay, from the perspective of a column player, what he really wants to do is to minimize. He wants the lowest value possible. He likes cells that have very small values. Okay, let's try to fill in the rest of the cells here. What should I put in the diagonals? A bunch of zeros, right? Because at least in the rock, paper, scissors game, it's a very particular game. When both players play the same strategy, then it's a tie. Okay, there's other games you could have played where if they play the same strategy, something else happens. Here's a game that the row player would really like to play. Is ones everywhere. Okay, so that's also a valid game. It's not the rock, paper, scissors game. This is has a particular structure. All right. So how about if the row player plays rock and the column player plays scissors? 1, right? So in by symmetry, put a -1 here. Okay. And last one, we have if the row plays scissors and the column player plays paper. Yeah, 1 and -1. Excellent. All right. So this is the so-called payoff matrix of the game. Why is it called payoff? Because you can imagine that they're betting money and they earn this much, okay? Or you can think about they just become happier by 1 unit, okay? So that's kind of their payoff. And so the row player wants to maximize his payoff. And the column player wants to what? Minimize, right? Minimize his payoff. Okay. Are all games zero-sum games? No, not necessarily. This is a particular structure we'll study today. Just for the record, people study all kinds of simultaneous two-player games that don't have to be a zero-sum. In such a case, what you do is you represent explicitly the payoffs of the two players. So you could have, I don't know, a game where it's top-bottom, left-right, and maybe if they both play in the top left, it's 1 and 2, right? It's like two different things. That meaning 1 for the row player and 2 for the column player. Here, maybe it's 3 and -1, 0 and, I don't know, 3, and -1, -1, right? So in a general two-player simultaneous game, it need not be zero-sum. Zero-sum denotes that the sum of the two entries is 0. Here we are being implicit about the fact that we have 0, 0, -1, 1, right? 1, -1. We're just kind of always having in the back of our head that the payoff of one player is the negative of the other. And if you sum them together, you get 0. In general, it need not be the case, though, and these are very natural, also very natural games, where you keep track of the utilities sort of separately, okay? This is a non-zero-sum game. But this is not what we study today. It was just sort of to contextualize a zero-sum. Okay. So are we together here? Questions about this? Okay. So what are all the strategies that a player could play, the role player could play in the rock, paper, scissors game? Are these the only options? Kind of yes and no, right? Yes, because, well, what else could he do, right? But no, like, there's also more, there's a richer set of strategies also. What could those strategies be? Yeah?
Rock, paper, or like some sequence of it?
Okay, so one could consider so-called iterated games, right? Where you play this game over and over, and you try to sort of learn from the other player kind of what they're doing, and you try to kind of counter that. People study these things. We're not going to study this today, okay? But it was a reasonable thing to say. Let's stick to one-shot game, right? Clearly, at the very end, when I actually sort of put down my hand, it's either one thing or another or another, right? But a priori, when I kind of, in my mind, I think of a strategy, do I really think of only rock, paper, and scissors? What's usually the best strategy to play in this game? Random, right? That's kind of cannot be beaten, right? So we'll see that in a moment, formally. So somehow, the set of strategies you play is not just play rock with probability 1, or paper with probability 1, or scissors with probability 1. In reality, when you think of a strategy, it's actually a distribution over your options, okay? So that's why typically one distinguishes the set of so-called pure strategies. So we have the pure strategies are just, this, in the end, kind of the buttons you could push, right? But as a player, you reason about mixed strategies. These are distributions over pure strategies. For example, playing a random strategy consists of picking at random a pure strategy and playing it, right? And then this means that you will have the payoff you will experience will itself be some random variable, and we'll want to study its expectation. Okay? So in this way, sort of the role player in general plays a mixed strategy that we can represent as a vector x1, x2, x3, which correspond to the probabilities that are assigned to rock, paper, and scissors respectively, right? So, and what are the constraints on x1, x2, and x3 such that this is a probability distribution? Right? It should be that they sum up to 1, right? And also that they are non-negative. Right? So in general, this is a strategy for the row player. And for the column player, it's basically the same thing, just we'll denote it using a different letter for just to kind of be clear about which player we talk about. We'll write y1, y2, y3, such that y1 plus y2 plus y3 equals 1, and they're all non-negative. Right? So this is really the space of strategies from which the players are thinking strategically from, right? So which mixed strategy should I play? Not so much which pure strategy should you play, okay? Now, in general, if row plays the mixed strategy X and column plays the mixed strategy Y, the expected payoff of the row player is what? We can write it as an expression, right? So like we want trying to understand what happens in the game, right? So now we have a row player that is playing some mixed strategy. The column player is playing some mixed strategy. Now intuitively, the outcome of the game is a random variable, right? It is, you know, this with some probability, this with some probability. Actually, let's assign probabilities to these. In terms of the xi, what is the probability that this is the outcome? I think the opposite, right? X3. I mean, this is X is for the row player, right? So this would be X3, right? And this has, and from the perspective of a column player, is played with, you know, probability Y1, right? So this happens with probability X3 times Y1, right? This will happen with probability X3 times Y2, right? X3 times Y3, right? And so on and so forth. So there are 9 outcomes that correspond to the 9 sort of products of, you know, these probabilities, okay? Now, in each of those outcomes, there is a particular payoff, right? So overall, what is the expected payoff? Yeah, I just do the weighted sum of all these things. That's all I really wanted to say. Okay, so just write the expression in general. The expected payoff is an expression that looks like this, right? So you sum over all the options for the row and for the column, and you typically the payoff matrix is denoted by U for utility. Okay. You look at the ijth entry, okay? And you multiply that by xi and yj, right? So this is the weighted sum of all the possible outcomes. In this particular case, there's 3 possibilities for y, and there's 3 possibilities for j. And there are 9 values of uij. Which one's those there? Okay? So this tells you for any sort of 2-player zero-sum game, if row plays X and column plays Y, this is the expected outcome. Okay? So, so here, now that we've written the expected payoff, we probably should come back here and change. So here, we didn't have mixed strategies in mind. So now we should revise this and say, look, the row player wants to maximize his payoff in expectation, right? Because in general, the payoff is a random variable. What does it mean to maximize a random variable? It doesn't mean anything. It's a distribution, right? So what you want to do is to maximize the expectation of that distribution, namely the expected payoff, right? And similarly, the column player wants to minimize his payoff in expectation. that's just saying that one of them wants this quantity to be big, and the other one wants that very same quantity to be small. Okay? By the way, you may wonder, why do we care about expectation as opposed to other things? Maybe the role player wants to make sure that U is never below 0. That's another reasonable thing, right? Like strategically in life, you also sometimes do this. When you don't care specifically about expectation of some event, you just care that some event is not worse than something. You're just fine with something being above a certain threshold, right? And in game theory, people study all kinds of other things too, right? So this is this is an agent that is called risk neutral, okay? Which means that all it cares about from a rationality perspective, when it thinks strategically about the game, is the expectation of an outcome. It doesn't care whether, with half probability it is, minus infinity, and half probability it is plus infinity, and they've averaged to 0, okay? Many of us would, right? And this is called risk aversion, which is a well-known sort of aspect of human strategic behavior. And people also study sort of risk-averse agents in games. But all I'm just saying is that looking at expected payoff is, to some extent, a modeling choice. Okay, it's not like you have a forced hand that you must look at that. Okay, does that make sense? All right. All right. Let's give an example of what happens in that game. Let's say that we fix X to be the random strategy, which is a third, a third, a third. Okay. And I fix Y to be a stubborn Caesars. Okay? Let's check what is the expected payoff. Also, we can just denote it U. Let's say that U is defined as this quantity. So how should I compute it? Just as an example. Excuse me? Right, so I start out, maybe it's easier to kind of, so Y is making our life easy because we can just ignore 2/3 of the matrix, right? It just says, since Y never plays on this side, I don't even need to look at what's there, right? Y always plays on this side. So I just need to look at this column, right? And X, assigning a weight of a third to each of the rows means that I just need to sum up things in this column with weight a third. Right? So it would be like 1 times a third times 1, right? Minus 1 times a third times 1 plus 0 times a third times 1. Okay? Now, these two equal. This is anyway 0, so you get 0. So this is saying that the expected payoff for the role player is 0. And actually, so is the expected payoff for the column player, also 0. Right? It's minus 0. OK. So this is an outcome of the game if they were to play something like this. Now, something I want you to observe is that in this particular game, the random strategy is not just an arbitrary mixed strategy. It actually has a very special property. Let's look at example again. Let's fix, again, the random strategy for one player. And let's parameterize the strategy for the other player. Okay, so the other player is going to play something that is y1, y2, y3. Okay, so a special case of this would be that one up there. But here I'm just saying, let's just see what happens if the second player, the column player, just plays some arbitrary mixed strategy against the row player's random strategy. Okay? And let's again compute U. Okay? So the formula up there says that we should sum up things this way. So let's write it. Sum over ij, uij, xi, yj. OK, what I've done so far, I'm just copying the definition. But notice that xi equals a third for any value of I, right? So I can rewrite this as saying, let's just sum over j, yj, OK? And then I have an inner sum over I. OK? So I'm just saying, just reorder terms. What is this value? Actually, I should put here third, maybe, just to make it clear. What is the value here? What does this say? Sum up what? So this says sum up things that are in a column, right? Sum up the values here, sum up the values here, sum up the values here, always with all the entries weighted by the same value. In this case, it's a third. So what do I get in each of these cases? 0, right? So the sum in every column of the entries is 0. So actually what we get here is sum of yj times 0, and that's just 0. This is curious, because somehow by playing this strategy, no matter what the other player does, you can ensure that your expected strategy cannot be worse than 0. OK? Like, you cannot do worse than 0. Now, there are strategies where you could do worse than 0 if you play them, right? So if you play, I don't know, if the other player knows that you're going to play scissors, it will play rock. And then you will get -1, right? But this strategy could be publicly known to the other player. Like, you can just tell, hey, column player, I'm going to play randomly, right? And there's nothing the other player can do to drive your utility below 0. OK, this is why playing randomly in rock, paper, scissors is actually not so much about strategy. OK? Kind of it gives you this guarantee. Now, could it be that there exists a strategy that has this similar property, but it guarantees you a utility that is bigger than 0? Could there be there is a strategy that is better than random? Yeah?
No, because in order to guarantee it, you'd also have to get bigger than 0 versus the 1/3.
Right. The column player could also play this strategy, right? And by symmetry, they would make sure that the utility cannot be higher than 0, right? Because they want it to go low. They want it to go low, right? But it can definitely make sure that it is 0 by just because this game is symmetric. So this reasoning tells us that actually playing randomly for both is actually the best they could do. OK? Because on the one hand, playing randomly for the row player ensures that things are 0. OK? It cannot get worse than 0, meaning lower than 0. And for the column player, playing randomly makes sure that things cannot get higher than 0, which he doesn't want to. OK? So somehow, now they're in this equilibrium where the row player wanted to push up, the column player wanted to push down, and now they met in the middle, and they each have these optimal strategies somehow. And so what we learn from here is that playing a third is optimal for both. OK, this was just an example. It is a somewhat degenerate because kind of things look literally the same from the row player and the column player, so they're actually playing the same strategy. So what I want to do now is to go another example that is not symmetric, OK, where we can see that it will be another instance where there is such a phenomenon, where the row player wants to push up, the column player wants to push down, they meet somewhere in the middle, and each have some strategy that, that achieves that. OK? Questions? Okay. So let's look at another example. And this time we're going to look at a game with two strategies for each player. There's going to be top, bottom, and left, right. And the numbers are going to be 5, -3, -1, and 1. OK? So first, let's just kind of play with this for a moment. Suppose a kind of row announces actually, I want to do it here. Suppose row says that he will play the strategy half-half. Okay, I just want to kind of work out what will happen with the random case for a moment. What should column play? Okay, let's just say that the row player doesn't want to be strategic today. He just says, look, column player, I'm going to play half and half on top and bottom. What should the column player do? Look, he has two options, right? He could play left, he could play right, or some mixed strategy between them. Does it make sense to play a mixed strategy in this case? Look, one of the two will be, one of the two will be lower, which is what he wants, right? So let's just compute that. If he plays left, what will it be his utility? Five -1, but not quite 4, right? Because I need to over 2, right? Right, because he finds himself here with half probability, right? Is it 5 -1? 5 -3, sorry. He finds himself here with half probability, right? What am I doing? Sorry. I had a minus. OK, good. All right, so he chooses this one. And then half probability will be here and half here, right? So we have 5 -1. We have 4 over 2. And this gives you 1, right? Or 2, sorry. Man. OK, sorry about that. Oh, wait, and for the right-hand side, right? So he will find himself with probability half and here with probability half. So we have -3. Plus 1 over 2, that is -2 over 2, and that's -1. Which of these two he prefers? R, right? Because, so column will pick this one. Because he wants to minimize, right? OK. Let's say that the column player let's see what happens on the other end. Suppose that the column player he will play. So anyway, I'm going this very slowly because in a moment it's going to get a bit more complicated. So what should row play? So he has two options, either top or bottom, right? Right? OK, so if he plays top, what will be his utility? I say 1, no? It's, if he plays top, it will be 5 with probability half and minus 3 with probability half. Right? So 5 minus 3, that's 2. Over 2, that's 1. Right? Do you agree? And if he plays bottom, it will be minus 1 with probability half and 1 with probability half. Right? And overall, that's 0. So he will pick this one. Okay? Rho will pick this one. So, OK, all I was trying to do right now was to see, let's see what happens if both of them play randomly. Before, it ended up playing randomly had a special property, right? It was a very special distinguished strategy. Now, looking at this game, there's no reason to believe that playing randomly is smart. OK? Here, I wanted to go through the computations to see in what way it's not smart. OK? Notice, if either of the players announces that they're playing randomly, the other player can force a certain utility. And these utilities are different. In one case, the utility is minus 1. In the other case, it's 1. So as is, it is not clear, this is not a proof, that playing randomly cannot be beaten by another strategy. Right? Here, because the two values met each other, right? Kind of each of them was proof that the others was optimal. Right? Whereas here, because these two values are not the same, I say, well, I don't know. Maybe there is some other strategy for the row player that regardless what the column player will choose is actually higher than minus 1. Right? And similarly here, it could be that there is some strategy for the column player that regardless what the row player will do, will be smaller than 1. Right? If this is the case for either player, it would be better to play those strategies. Right? OK. So now I want to actually put down a strategy that has this property. And we'll see that they will meet somewhere between minus 1 and 1 at the same point. By the way, what does this smell like? We saw something less. It's like duality, right? This is a form of duality. We'll see that later. Okay? All right. So let's sort of look at, so that this were the random stuff, right? So here, let's say that rho announces a 1 over 5 and 4 over 5. OK? Then for column could either do left or right. Right? So in the case of 5, so in the case of left, it would be 5 with probability 1 over 5 and minus 1 with probability 4 over 5. Right? So it is 5 times 1 over 5 minus 1 times 4 over 5. What is this equal to? 1 over 5, right? OK. If he chooses right, it will be minus 3 with probability 1 over 5 and 1 with probability 4 over 5. What is this equal to? 1 over 5 also. OK. Right. We have understood, and what will column play? It doesn't matter. OK? He can pick either. All right. Now let's say that, so that's for the row. Now let's say that column announces two over 5 and 3 over 5. OK? For row, there are two options, either top or bottom. Okay? Now, in the top case, it will be 5 with probability 2/5, right? And -3 with probability 3/5, right? Okay? So 5 times 2/5, and then -3 times 3/5. What is this equal to? 1/5. And in the bottom case, it will be -1 times 2/5 and 1 times 3/5. What is it equal to? 1/5. OK, so for this funny strategy that we'll see in a moment how to derive, what's happening is that the two sides are balanced, right? On the one hand, the row player has a strategy that he can make sure that regardless of what happens for column, the utility that he gains cannot be worse, meaning smaller, than 1/5. On the other hand, there is the column player also has a strategy, right? Different strategy in this case. But it also has the property that regardless of what row does, he can make sure that the utility that it gets is no bigger, right, than 1/5. So each of these prove that the other is optimal. OK? So these are kind of strategies that are analogous to the random ones for rock, paper, scissors. OK? Now, how do we find these strategies? OK? So what I want to do now is I want, for this game, show how we could mechanically derive these. OK? And then we'll try to take a step back and see what happens for every game. But does it make sense what we did here? What we did was we looked at random strategies, just as a guess. Didn't end up being a good guess for this game. Then I put down some magical strategies that, for a moment, it looks like they are out of a magic hat. But we'll define them. We'll show how to kind of derive these mechanically. But we have verified that in this game, there is also so-called solution, right? Each player has a strategy that is best to play. OK? OK? Are you just mesmerized, or it makes sense? Okay. Yeah, there's a question. The two values? The two values, yes, they have to be the same.
Also with like the row and for the column. So for one fit, one on the top and one fit on the row.
Yes, they will be, because we'll show in a moment. Yeah. Yeah.
Why does it mean the same
Because, so remember, the row player wants to increase utility, right? And the column player wants to decrease utility. If among all the things the row player can do, there is a strategy that makes sure that regardless of what the column player does, the utility cannot be worse than 1/5. And at the same time, among all the things that the column player can do, there is one strategy that ensures that regardless of what the row player does, the utility cannot be higher than 1/5. OK? Then each of these proves that for either player, there is no other strategy that will guarantee a utility that is higher for the row player or lower for the column player than 1/5. OK? That makes sense? Yeah.
Is there like, how do I know that there's no way to like come up with a strategy where the left and right are like both greater than 1/5?
Because you can look at the other player, right? So here you say, how do I know that the row player cannot have some other magical strategy, x1 and x2, that makes sure that left and right are both higher than 1/5? Well, one way is to notice that the column player could, among all the things he can do, he can play this strategy that says, regardless of what the row player does, the utility cannot be higher than 1/5. OK? Kind of they bound each other. OK. All right. So now let's try to see what happens generically here by trying to derive that strategy as the but try to derive those strategies as the answer of optimization problems. So I'm going to do it by removing this stuff. So in general, for this example, I mean, we'll see in a moment for all games. For the example up there, what we have is that the row player announces some magical strategy that we don't know. So let's give it the name, x1, x2. Right? We want to figure out what is x1 and x2. Now, a column has two options. So announcer, we can say then column peaks either left or right. Let's figure out what is the expected utility in the left case in terms of x1, x2. What should it be? So now we have a parameterized family, right, of strategies, x1, x2. Row said he's going to play this strategy. Column is strategizing. He's wondering, should I pick left or right? In order to strategize, he has to compute the expected utility in this case and expected utility in this case. Okay? What's the expected utility in this case? 5x1 minus x2. Yeah, 5x1 minus x2. Why? Because it's in top with probability x1, in bottom probability x2. If he picks L, then it will be 5x1 minus 1 times x2. And the other case is what? So it's minus 3 x1 plus x2. So which one should column pick? Whichever is smaller. So let's say column picks the smaller. Maybe they're equal, and then it just doesn't matter, right? But so picks the smaller. Smaller of the two. OK. So the utility that we get is minimum of 5x1 minus x2 and minus 3x1 x plus x2. Right? So it picks the smaller of the two. It means that in the end, if Rho has announced this thing, then the utility he will experience at the end is this expression. Right? Just like similarly here, when there was two options, 2 or minus 1. The minimum is minus 1. So there will be a utility that he will experience because column will pick that one. OK? Oh, wait, that's on one side. Let's say that Rho announces y1, y2. OK? Then not Rho, sorry, column. Column announces y1, y2. Then Rho picks either top or bottom, right? So in the top case, what does he experience? Yeah, 5y1 minus 3y2. OK. And in the bottom case, it will be minus y1 plus y2. OK. And Rho picks the bigger one. So the expected utility in this case is what? The maximum of this expression, 5y1 minus 3y2, or minus y1 plus y2. OK? Now, what we want is we want for these two expressions to eventually kind of equal one another. So want them equal. Right? That's kind of what happened there, right? Because whenever they're equal, it means that for a strategy x1 and x2 that equals this, for which this equality holds, and for a strategy y1, y2 for which the equality holds, okay? Then that is the solution of the game. Okay? What I want to do now is I want to show you that this on its own is a linear program, and that this on its own is another linear program that in fact is its dual. The fact that they have the same optimum is duality. Okay? And to find either of the strategies, you can just solve the corresponding linear program. Okay? This might look a bit funky because, look, this doesn't look so linear, right? Right? Mean is not a linear function. And max is not a linear function. So what, like other things are linear. That looks like a linear thing. That's a linear thing. Right? Forget what it is, but linear programming, you want to look for linear things, right? So we have to somehow figure out how to deal with the notions of mean and max, okay? But it will be fine. But do we see that sort of all I've done is I've taken the reasoning that now we've done once for the rock, paper, scissors, twice for this other problem. Now we're done in a fourth time, okay? This fourth time, now we're doing it in general, okay? All I'm doing is just the same thing over and over because I want it to stick, okay? All we're doing is we're just doing it in general right now. Do we agree? Yeah? I didn't catch the start. It's a great question. So if I announce a strategy, a mixed strategy, say that I'm the row player. I have just announced x1, x2. And I'm wondering, what will column pick? After all, column has all mixed strategies at his disposal to play. Why would he limit himself to just picking left or right? Does anybody know an answer? Yeah? Right, so you're taking a convex combination of two numbers, right? It's a convex combination, I don't know, of 6 and 9, right? And any convex combination cannot be higher than 9, right? So in principle, he is considering all the mixed strategies, but because probability distributions are just convex combinations, he can just pick a vertex of this convex combination to be the one that is the highest strategy. Okay? Good question. Okay, so now I'm going to write a linear program for each one of these things. I'll do it underneath them. All right, so let's look at the left-hand side. I want to write a linear program, okay? So let's call it the linear program for the row player. So what he wants to do is he wants to minimize something, but this something is not a linear function, okay? So here's a cute trick that might come in handy a few times. So he's actually going to maximize some other variable, okay? And the variable, let's call it z. He's going to maximize a variable z. We're going to make sure that z is no more than both 5x1 minus x2 and z is no more than minus 3x1 plus x2. x1 and x2 are also variables. They just happen to not appear in the objective function. So you can think about it as kind of plus 0 times x1 plus 0 times x2. They're also variables, okay? So I'm just put that in parentheses. But really, it's maximizing z, OK? And then also, we're going to say that x1 plus x2 equals 1. And x1, x2 are sort of non-negative. Now, of course, this is just saying that x1, x2 is a probability distribution, is kind of valid as a mixed strategy. But can anybody say, like, why would this, so you could call it a small gadget of constraints, actually implement this desideratum? Yeah.
In order for something to be less than the minimum of two expressions, it's enough to say that it's less than both of them.
Yeah. Right. So look, if you want to maximize this one, OK, and you are, say, strictly below both of them, well, that you're definitely not at optimum. So you are only at optimum when at least one of these is an equality. If one of these is an equality, the other one cannot be smaller, right? So you just match the minimum. OK? So that's it. Yeah.
Why can't you just do what we did in the previous example, where you set them equal to each other, and or you where you know that both of them should be equal to each other to get the maximum?
Yeah, and this is what you would, yes, excellent.
Maybe at the boundaries also when x1 is 1 and x2 is 0, or x2 is 1 and x1.
We could just set them equal to one another, right? And this would be fine. And this is what you would do, I guess, you know, in a homework or in an exam. Right now, I was just trying to emphasize that I can, if I want, write this as a linear program, OK? In a way that I can take its dual. But otherwise, yes, what we were doing there was anytime the two sides are unbalanced, there is an opportunity for the other player to gain something over me. So let me make it sort of like make them equal, right? Now, in general, when you have a different number of strategies, things may not be so clear. So for example, suppose that the top player here, suppose I added another strategy for the column player, and I leave the number of strategies for the row player the same, right? So I kind of extend this, and there is left, right, and I don't know, other. OK? What you would have here is actually three options, right? So you have a linear expression in x1 and x2, another linear expression x1, x2, and another linear expression x1, x2. It could be that you're actually not able to solve this as a linear system of equations because it could be over-constrained, right? Because you have three linear equations that you want them all to equal one another, right, in two variables. So in two-player games with each of them two strategies, just setting the two sides are equal is great, and it's the only way to solve it. But in general, right, you can't just set them all equal to one another. You may not be able to resolve it that way. Okay? In that case, sort of what you actually have is a linear program. But it's a great question. Okay. But otherwise, do we agree that this is a linear program whose solution is sort of something that satisfies this, this quantity, right? Okay. So then we also have the linear program for the column player. So we're going to use also a so-called auxiliary variable, min w. Okay? And of course, implicitly here, we also have 0 times y1 plus 0 times y2, which are, it is a linear function of the variables w, y1, and y2, except that y1 and y2 are not participating. Such that, and here I have sort of the other trick. Now I want w to be at least 5y1 minus 3y2, and w to be at least minus y1 plus y2. Okay? And then, similarly to there, I need to make sure that y1, y2 is a valid mixed strategy. So I have to say that it sums up to 1, and y1, y2 is greater than or equal to 0. Now, in this case, what we want to minimize, we want w to hit one of these two, right? If it hits one of them, the other one cannot be higher, right? I would have hit it earlier, okay? So w really represents, it's an indirect way to talk about the maximum of these two things, right? Now, these are two linear programs, and you can see, if you think of the coefficient matrix, which is 5 minus 1 minus 3 and 1, and this one, they're actually transposes of one another, which is what you would expect in so when you take the dual, okay? Now, of course, when you take duals, you also have to massage things a bit, and you might not exactly get that one, but the point is that, at a high level, these are duals of one another, okay? All right, so let me just pause for a moment, okay? And say that in general, we're gonna see now what happens in a general game where you have an arbitrary number of strategies for the row player, an arbitrary number of strategies for the column player. What we're trying to say is we want to mechanize, okay? We want to reduce finding the best strategy for either player to a linear program, which you can then solve, using an algorithm for any linear program, okay? Now, for concrete games, you can try to solve it by hand like we did there, right? But as the number of strategies grows, and especially when they're kind of unbalanced, okay, then it becomes pretty messy to do it by hand because you're basically trying to solve a linear program of some sort by hand. Does this make sense? Okay. All right. Here, let's get rid of this stuff. All right, so before we get there, now, did more questions arise in the meantime? Are things clear? How many people are nodding? There's a question somewhere? Okay, no? Are things really clear? Okay, good. All right, so I was trying to go slow. Hopefully it got across. I encourage you to, to try this, I think this derivation up to here is pretty clear, okay? I guess maybe it might be worth to try offline, kind of in a dark corner somewhere, sort of when everything is silent, just sort of verify that these linear programs are in fact just representing those optimization problems. Okay, so before we get to something, but a bit even messier, okay? Let's talk about something stupid again. So we're talking about games today. So how do you say game in Italian? No, juego is in Spanish. But almost, actually, right? So they're pretty close. Does anybody know? How do you pronounce this? Gioco, right? So we've talked about the I before. It's silent, okay? It's just there to make the G a J, right? So this is gioco. It's a game. And it's pretty much literally the same. Like it either means those physical objects that kids play with. It could mean video games, or it could mean abstract games like these things. So it has pretty much similar semantic span. OK. Let's try something else with around the G side of things. There's an expensive car that has a G in its name. Very expensive car, Italian. Starts with L. La. How does it? It doesn't finish here, by the way. Like. And then, so we get to the critical part here. H, right? What does the H do there? It makes the G hard, okay? Like in my last time, just for C, right? So this is actually Lamborghini. Please don't say Lamborghini, like it's terrible. Okay, so, okay, more G trickery. There is there's an Italian food where there's this flat pasta, right? You know, layer after layer, and in between you put lots of meat, right? Right, so there is more trickery here, right? So the N, so the G becomes, you know, it gets palatized. It's not G, it's not lasagna, right? It's a lasagna, right? So this is kind of like the Spanish ñ. Okay, so getting comfortable with G's. Okay, how about another one? What is, I mean, how do you pronounce this? Huh? Both are R's, sorry, they're not T's. Yeah, they're short. Yeah. How do you pronounce this? Girare, okay? So the G here is soft because it's followed by a soft vowel, okay? There are 3 strong vowels, A, O, and U, right? And then there are 2 soft vowels, E and I. It's in many languages it's like that. So here it's girare. That's why there's an H here to make it G, right? Otherwise it would have been G, like here. Girare means to turn around. It's a verb, okay? Okay, so much for that. Now that you're relaxed a bit, let's look at the general case. Okay, so let's try to see what happens, how to write this linear program in the general case, okay? Just so we see the pattern, okay? So now we have the game is given as just the matrix, right? Uij for I going from 1 to m, and j going from 1 to n. Okay, so this is a general 2-player zero-sum game, right? Just we got a matrix of things. Okay, now a row strategy is x1 through xm, right? And a column strategy is y1 through yn, right? Do we agree? This is like a general formulation. If you give me a game that looks like this, in general, I can play as a row player any out of the m options, right? And any out of the n options. Okay, and for any particular actual outcome, I comma j, there is a corresponding payoff, okay, for the row player. And the row player wants to maximize this thing, and the column player wants to minimize it. All right, so let's try to see kind of what happens in general. So say that row, we're going to do it for the 5th time, okay? So hopefully it will stick this time. Row announces x1 through xm, okay? Then the column wants to minimize the expected payoff. So he's going to pick a, how to call it? I'll call it J star. We'll pick J star that is minimum among what is the set within which he wants to minimize over? Right, so he has options that look like those, right? Some of them will be, I don't know, 5x1 minus x2 plus, I don't know, x3 minus 7x4, blah, 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 right? That's one option. And then there's another one, right? That's another option. So here's a useful notation that you can use. He can say the minimum among u, x, comma 1, up to x, comma m. So what does it mean that I plug in x into u? It means that I take the expected thing across the row, right? Sorry, column. This is saying take the weighted sum of things in the first column, and take the weighted sum of things in the second column, right? Blah, 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 up to weighted sum of things in the last column, right? Row player will pick a column, which one? J star, that is minimum among these, right? Okay. So, so how do we write? So then we're going to say that the row, so the solution is, let's just write the solution for the row player, is x star, okay, which is, you know, x1 star up to xm star, defined as follows. So here I'm not writing the linear program yet. I'm just telling you what it will pick, right? So what will row player do? He wants to push up this minimum, right? So right now he's saying, oh, if I announce x, what I will experience is the minimum of these numbers. OK, but that was just a thought experiment about a particular x. I could have done any x, right? I should pick the x star that maximizes the minimum of these things, right? So x star is the arg max over x, is whatever maximizes things over x, of the minimum over j, right, of this thing that I wrote up here, x, comma, x, comma, j. There we go. Right? Here is the minimum for a given particular x, right? So this is, in general, the definition of the solution for the row player's strategic problem, right? Do we agree? Yes?
Why don't row announce the strategy? Why don't they just like not say anything?
Yeah, I mean, it was a simultaneous game after all. All of these are thought experiments, right? So we're trying to say, if I were to announce this, then what would the other person do, right? This is normal, right? So when you play chess, for example, right? And you think in your head, oh, what would happen if I were to do this move, right? You're not telling the other component, like, here's the move, right? You're currently just evaluating options, right? It's similar. I'm saying, let me evaluate option x prime, option x double prime, option triple prime, right? And then after evaluated all of them, I pick the best one, right? It is analogous to chess, right? So you typically, OK, chess is a iterated game, so it actually goes very deep, right? You can't typically get to the very end, right? But you're thinking these scenarios in your head. You're not telling the other person these scenarios. You're just thinking them in your head.
This game is like a simultaneous game, right?
It's a simultaneous game.
Both do it at the same time.
Exactly, at the same time.
Like, with chess, it's like first I do this, then they play.
Right, it's not a turn-based game. This is a simultaneous game, which I already erased, right? And so they have to play at the same time. And the strategic choice of row is to say, look, if the column player were to correctly guess that I were playing this, right, then he would do that, okay? But then let me just pick the best choice under the assumption he correctly guessed, okay? And because in the end, whatever I get like this is anyways whatever is forced upon me by the other player, then that's the optimal solution, okay? It's a good question, right? By the way, things get really messy when you study like sort of, so this is the area of game theory, and specifically when you start tying it to linear programming, this becomes so-called algorithmic game theory. And sort of zero-sum, two-player simultaneous games are, it's a very simple sort of notion. It gets pretty messy when you start having sort of the strategic reasoning is kind of, yeah, like not everything has nice solutions like these, okay? Now, what I want to do, so and of course you can do the same for the column player, and you kind of flip all the right things. He wants to maximize, you pick the maximum, and you pick the argmin, okay? What I want to do is I want to write the linear program at least for the row player, okay, in the general case. So the linear program for the row player, which is the one that you solve, he's going to maximize z, and again, plus implicity 0x1 plus 0x2, and so on, subject to z is at most ux1, z is at most ux2, right? Z is at most ux. Did I use m here? I should have used n here. Nobody told me. xn, okay? So these n constraints are analogous to those, okay? And then we also need to make sure that the sum of x1, x2 up to xm equals 1, and then also that x1, x2 up to xm are non-negative, okay? And again, this thing is kind of reasoning about the, where you go, the minimum among u, x, j, among all j. Okay? So this is how you would find, in general, by solving this linear program, the value of the optimal strategy. Okay? And I'm not going to sort of flip all these things. There is the duality theorem was actually first proved in this special case. And it's called the minimax theorem. Okay? Because these strategies, this is actually the maximin strategy. You sort of maximize the minimum. And the other player, it minimizes the maximum. And the minimax theorem says that these two values are the same, which is a special case of the duality theorem for games. Okay? So